Hello everyone. Today we are going to analyze this beam using flexibility matrix method. Before analyzing, let's see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is uniformly distributed load 24 kN per meter acting for the full span. In the span BC, there is a point load 50 kN acting at 2 meter from the point B. In the point A, there is a fixed support. In the point B and in the point C, there are roller supports. Span AB is 4 meter long and span BC is 5 meter long. In this beam, the number of unknown reactions and moments are 4. They are MA, RA, RB and RC. The available equilibrium equations are 2. Summation of moments is equal to 0 and summation of vertical forces is equal to 0. So the degree of static indeterminacy is equal to 4 minus 2. We will get 2. From this beam, let us release MA and MB. When we release MA and MB, this continuous beam becomes two separate simply supported beams. So this statically indeterminate beam is made into two statically determinate beams. These beams are called the released structure. We have made the released structure. Now let us make the coordinates diagram. In this analysis, there are two coordinates. In the point A and in the point B, we are having the coordinates because in these points only we have removed the moments. In the point A, let us keep the coordinate in the clockwise direction. In the point B, the coordinate will be acting in both of the directions. For the beam AB, it will be acting in the anticlockwise direction. For the beam BC, it will be acting in the clockwise direction. Now let us see the formula to calculate the moments. P matrix is equal to delta matrix inverse into delta matrix minus delta L matrix. Here P matrix is the final moments or forces, delta matrix is the flexibility matrix, delta matrix is the final displacements, delta L matrix is the displacement in the coordinate direction. Inside the P matrix, we will have MA and MB because these are the moments we have released. Inside the delta L matrix and delta matrix, we will have two values because in this analysis there are two coordinates. In this formula, first let us make the delta L matrix. In this analysis, we have released the moments, so the displacements will be the slopes. We have to calculate the slope values using the conjugate beams. Using the loads, we can make the conjugate beams. First, let us take AB. In AB, UDL is acting for the full span. In a simply supported beam, if UDL is acting for the full span, the formula to calculate the maximum bending moment is WL square upon 8. Here W is 24, L is 4. When we apply the values inside the formula, we are getting 48. Using this value, we can make this diagram. We know that for the UDL, the bending moment diagram will be in the shape of parabola. Now let us take the span BC. Here there is a point load. This point load is not acting on the center. The formula to calculate the bending moment is WAB upon L. Here W is 50, A is 2, B is 3, L is 5. When we apply the values inside the formula, we are getting 60. Using this value, we can make this diagram. We know that if the point load is acting, the bending moment diagram will be in the shape of a triangle. Also, we know that in the conjugate beams, we have to divide the moments by EI. We know that inside the delta L matrix, we will have two values, delta 1L and delta 2L. Delta 1L should be calculated from the first coordinate, that is in the point A. Delta 2L should be calculated from the second coordinate, that is in the point B. Here there are two conjugate beams, A dash B dash and B dash C dash. We know that delta 1L and delta 2L are the slopes. First, let us calculate delta 1L, that is the slope in the point A. In the conjugate beam, the shear force is the slope. So, to calculate the slope at A, we have to find the shear force at A dash in the beam A dash B dash. In the point A dash, the shear force will be the vertical reaction RA dash. It is a symmetrical diagram, so we can easily calculate RA dash and RB dash by taking the total load. In this conjugate beam, the total load is the area. The area formula for this parabola is 2 upon 3 into breadth into height. Here the breadth is 4, height is 48 upon EI. So the area is 2 upon 3 into 4 into 48 upon EI. When we divide this area by 2, we will get RA dash. Let us apply this value for delta 1L. Now let us calculate delta 2L. For that we have to find the slope in the point B. So we have to find the shear force in the point B dash. Here the shear force is RB dash. We have to calculate RB dash two times. First in the beam A dash B dash, then in the beam B dash C dash. In the beam A dash B dash, we know that it is very easy to calculate RB dash. We have to divide the total load by 2. After calculations, we are getting 64 upon EI. Now let us calculate RB dash in the beam B dash C dash. This loading is not symmetrical. So to calculate RB dash, we have to take moment about C dash. In this case, we are moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. RB dash is acting towards the point C dash in the clockwise direction, so it will be positive and the distance is 5. So 5 RB dash. This UVL is acting towards the point C dash in the anticlockwise direction, so it will be negative. For this UVL loading, we have to multiply the area with the centroid distance. The area formula for the triangle is half into breadth into height. Here the breadth is 5, height is 60 upon EI. So the area is half into 5 into 60 upon EI. Now we have to calculate the centroid distance. We are taking movement towards the right side. So we have to select the centroid distance towards the right. For this kind of triangle, the centroid distance towards the right is L plus B upon 3. Here L is 5, B is 3. So the centroid distance towards the right is 5 plus 3 upon 3. After the calculations, we are getting RB dash 80 upon EI. For delta 2L, we have to add these two values. After adding, we are getting 144 upon EI. In the delta L matrix, let us apply the values of delta 1L and delta 2L. 1 upon EI is constant. Let us keep it outside. Alternatively, using these formulas, we can easily calculate the reactions. By doing so, we can save a lot of time. First, let us take the beam A dash B dash. In this beam, UVL is acting in the parabolic shape. The formula for the reactions are WL upon 3 and WL upon 3. Since it is symmetrical, we are having the same formulas for the reactions. Using the formula, let us calculate RA dash and RB dash. Here, W is 48 upon EI, L is 4. When we apply the values inside the formulas, we are getting RA dash and RB dash. Now, let us take this beam. Here, we have to calculate RB dash. The formula is W upon 6 into L plus B. Here W is 60 upon EI, L is 5, B is 3. When we apply the values inside the formula, we are getting 80 upon EI. For delta 1L, we have to apply the value of RA dash. For delta 2L, we have to add these two values. After adding, we are getting 144 upon EI. So, using the formulas, we can easily calculate delta L matrix. In this formula, we have calculated the delta L matrix. Now let us calculate delta matrix. If in the beam there is overhanging, we have to calculate the delta matrix. Otherwise, we can simply enter 0. In the given beam, there is no overhanging. So we can just enter 0, 0 inside the delta matrix. Same like delta L matrix. Inside the delta matrix, we will have two values because there are two coordinates, but both of the values are 0 because there is no overhanging in the given beam. In this formula, we have calculated the delta L matrix and the delta matrix. Only one is remaining, that is the flexibility matrix. Now let's see the size of the flexibility matrix. For 3 coordinates, it will be 3 by 3. For 2 coordinates, it will be 2 by 2. For 1 coordinate, it will be 1 by 1. In this analysis, there are 2 coordinates. So, the size of the matrix will be 2 by 2. Inside the matrix, we will have 2 rows and 2 columns. In this matrix, now let us calculate the first row. For that, we have to apply unit movement in the first coordinate. Let us apply the unit movement in the first coordinate. The first coordinate is in the point A. So, we have to apply the unit movement in the point A. When we apply the unit movement, here the movement will be 1 and here it will be 0. Using that, we can make this a diagram. We know that in the conjugate beam, we have to divide the moment by EI. Here the moment is 1, so we are dividing the moment by EI. Here for delta 11, we have to calculate RA dash. For delta 12, we have to calculate RB dash. First, I am going to calculate RA dash. For that, I am going to take moment about B dash. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. This RA dash is acting towards the point B dash in the clockwise direction. So it will be positive and the distance is 4 meter. So 4 RA dash. This UVL is acting towards the point B dash in the anticlockwise direction. So it will be negative. For the UVL, we have to multiply the area with the centroid. We know the formula for the area of a triangle, half into breadth into height. Here the breadth is 4, height is 1 upon EI. Using that, we can calculate the area. Then we have to calculate the centroid towards the right. In this kind of triangle, the centroid towards the right is 2b upon 3. Here the breadth is 4, so the centroid distance towards the right is 2 by 3 into 4. After calculations, we are getting RA dash. For delta 11, let us apply this value. Now let us calculate delta 12. For that, we have to calculate RB dash. We have to calculate RB dash only in the beam A dash B dash. In the beam B dash C dash, there is no load, so we don't have to calculate RB dash in the beam B dash C dash. Let us calculate RB dash in the beam A dash B dash. RB dash can be calculated easily by taking the total load. Here the total load is the area. From the area we have to subtract RA dash. Finally we are getting RB dash, which is equal to 2 upon 3 EI. For delta 12, let us apply this value. In the flexibility matrix, now let us make the second row. For that, we have to apply unit moment in the second coordinate. When we apply unit moment in the second coordinate, here the moment will be 1 and here it will be 1. Here it will be 0 and here it will be 0. Using that, we can make this diagram. Now let us calculate delta 21. For that we have to find RA dash. To find RA dash, I am going to take moment about B dash. RA dash is acting towards the point B dash in the clockwise direction, so it will be positive and the distance is 4. So 4 RA dash. This UVL is acting towards the point B dash in the anti-clockwise direction, so it will be negative. For the UVL, we have to multiply the area with the centroid distance. We know the area formula for the triangle, half into breadth into height. Here the breadth is 4, the height is 1 upon EI. So the area is half into 1 upon EI into 4. In this triangle, the centroid towards the right is B upon 3. Here the breadth is 4 meter. So the centroid is 1 upon 3 into 4. Finally, for RA dash, we are getting 2 upon 3 EI. For delta 21, let us apply the value of RA dash. Now let us calculate delta 22. For that, we have to find RB dash. We have to find RB dash in both of the beams. First, let us find RB dash in the beam A dash B dash. Here we can easily calculate RB dash by taking the total load. Here the total load is the area. We have already calculated the area in the previous step. The total load minus RA dash, we will get RB dash. Now let us calculate RB dash in the beam B dash C dash. For that I am going to take moment about C dash. RB dash is acting towards the point C dash in the clockwise direction. So it will be positive and the distance is 5. So 5 RB dash. This UVL is acting towards the point C dash in the anticlockwise direction. So it will be negative. For this UVL, we have to multiply the area with the centroid. The area is half into 1 upon EA into 5. The centroid distance towards the right is 2b upon 3. Here the breadth is 5. So the centroid is 2 upon 3 into 5. Finally we are getting RB dash. Now let us add these two values. After adding, we are getting delta 22. In the flexibility matrix, we have calculated both of the rows. 1 upon EI is constant. Let us take it outside. We know that it is slightly difficult to make the flexibility matrix because we have to take moment on both the sides. If you feel that it is very difficult, we can use formulas and find out the matrix very easily. Using the formula, let us calculate the first row. Here we need to calculate RA dash. The formula is WL upon 3. Here W is 1 upon EI, L is 4. When we apply the values inside the formula, we are getting 4 upon 3 EI. Now, using the formula, let us calculate RB dash. The formula is WL upon 6. Here, W is 1 upon EI and L is 4. When we apply the values inside the formula, we are getting 2 upon 3 EI. Let us apply these two values for delta 11 and delta 12. Now, using the formulas, let us make the second row in the flexibility matrix. First, let us calculate the reactions in the beam A dash B dash. The formulas are WL upon 6 and WL upon 3. Here, W is 1 upon EI, L is 4. When we apply the values inside the formulas, we are getting 2 upon 3 EI and 4 upon 3 EI. In the second beam, we have to calculate RB dash. The formula is WL upon 3. Here W is 1 upon EI, L is 5. When we apply the values inside the formula, we are getting 5 upon 3 EI. For delta 21, we have to apply RA dash. For delta 22, we have to add these two values. After adding, we are getting 3 upon EI. So, using the formulas, we can easily make the flexibility matrix. In this formula, we have calculated everything. Let us apply the values. We can add these two matrices. After adding, we are getting this. 1 upon EI inverse is equal to EI. Then we can eliminate this EI and this EI. For this matrix, we have to find the inverse. We can apply all of the values inside the calculator and find the inverse. If you do not know how to find inverse in the calculator, see the description below. Click the link and watch the video. I have used the calculator and got the inverse. Then we have to multiply these two matrices. After multiplying, we are getting MA and MB. So in this analysis, we have calculated both of the moments. In this analysis, we have calculated both of the moments. Now let us calculate the vertical reactions. For calculating the vertical reactions, we have to split the beam as per the spans. Here we are having the spans AB and BC. So we are splitting the beam into two parts, AB and BC. In the span AB, there will be two moments. MA will be acting in the anti-clockwise direction. MB will be acting in the clockwise direction. In the span BC, there will be one moment. MB will be acting in the anti-clockwise direction. Now, let us take the span AB and calculate the reactions. We already know there are two moments, MA which is acting in the anti-clockwise direction and MB which is acting in the clockwise direction. In this span, first I am going to calculate RA. For that I am going to take moment about B. In this case I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction. So it will be positive and the distance is 4 meter. So 4 RA. The UDL is acting towards the point B in the anti-clockwise direction. So it will be negative. For the UDL, we have to multiply with the distance and distance by 2. So 4 into 4 upon 2. Then there are two moments. The moment 27 is acting in the anti-clockwise direction, so it will be negative. The moment 42 is acting in the clockwise direction, so it will be positive. After the calculations, we are getting RA, which is equal to 44.25 kN. Now, using the rule, summation of vertical forces is equal to 0, we can calculate RB1. Here there are two upward forces, RA and RB1. They will be positive. The UDL is acting downwards, so it will be negative. In the case of UDL, we have to multiply with the distance to get the total load. Here we can apply the value of RA, which we already calculated. In this way we can calculate RB1, which is equal to 51.75 kN. Now let us calculate the vertical reactions in the span BC. In the span BC there is a moment MP which is acting in the anticlockwise direction. In this span, first I am going to calculate RB2. For that I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5, so 5 RB2. The point load 50 kN is acting towards the point C in the anticlockwise direction, so it will be negative and the distance is 3. Then we have one moment 42 which is acting in the anticlockwise direction, so it will be negative. After calculations we are getting RP2 which is equal to 38.4 kN. Now let us apply the rule summation of vertical forces is equal to 0 to calculate RC. RB2 and RC are acting upwards, so both of them will be positive. 50 kN is acting downwards, so it will be negative. Then let us apply the value of RB2. Finally, we are getting RC, which is equal to 11.6 kN. In the point B, we have calculated the reaction 2 times. Let us add both of them. After adding, we are getting RB, which is equal to 90.15 kN. Now we are going to draw the shear force diagram. Before drawing the diagram, let us calculate the shear force values. I am going to calculate from the point A and towards the point C. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. You can see the calculations. Using the values, we can make the shear force diagram. Now we are going to make the bending moment diagram. Before drawing the bending moment diagram, first we have to make the free moment diagram, then end moment diagram. Later we can combine both of them to get the bending moment diagram. For drawing the free moment diagram, we have to assume every span as a separate simply supported beam and calculate the moments. Previously, we have already calculated the moments. Using the values, we can make this diagram. We have already seen that. Using the end moments, we can make the end moment diagram. Then we have to combine both of the diagrams. Wherever they are acting alone, without mingling, we can mark the values with the signs. Here the end moment diagram, here the free moment diagram, end moment diagram, and finally the free moment diagram. Wherever they are acting together, we are not marking anything, we just keep the space empty. Now we are going to end this session. Thank you for watching this video.